Welcome to this week's podcast episode of Decarb Connect. My name's Alex Cameron, and I am here this week with Trevor Best, who is CEO and co-founder of Syzygy. Syzygy is kind of fascinating to me on a number of levels. So number one, based in Houston, which of course was always historically known as the big epicenter of all things oil and gas, and is now key center for clean tech and energy transition IP. And Syzygy is one of a number of early stage or relatively early stage disruptors calling the city their home. So it's kind of interesting on that angle, but also it's the first time we've featured anything about photocatalysis. So Trevor, welcome. Perhaps you could kick us off by just telling us a bit about how have you ended up here and now, and then we'll explore the technology and what Syzygy's up to a bit more.
Hello, Alex. It is fantastic to be here on the podcast today. And I would love to tell you about how we ended up here and now. And so, to understand Syzygy's journey, we've got to go a few years back. My co-founder and I were working in the R&D side of completions in the oil and gas industry. So subsurface, getting oil out of the ground. Through R&D work, very familiar with developing new products, bringing new technologies to market, et cetera. I was responsible for quality in the invention process. And so I had high-level cockpit view, and my co-founder, Dr. Suman Kadiwada, was a PhD material scientist who understands kind of the ins and outs. We really wanted to participate in the energy transition. This is back before it was called the energy transition. And we actually went searching for a technology. We took our learnings, we went searching for technology. We developed this framework called technology, market, and impact. And we eventually came across this photocatalyst technology at Rice University. We used, the learnings we'd gotten from developing, R&D products over the years to assess it. And it turned out it was truly amazing. So I decided to leave our jobs and start the company. Since then, since taking it out of the labs at Rice to today, we've scaled up the technology about 500,000x, and we need another jump of 20 to 40x, and then we're ready to get into the market. We've fundraised very successfully, and we have the money to take that last jump. So now we are in the process of working with customers and trying to sign first project agreements, et cetera. It's pretty exciting.
And we'll come back a bit to that search for the technology a bit later, maybe, but tell us then, so photocatalysis, it's not a technology we've featured before. It was totally new to me when you and I first connected. Talk us through, and bear in mind the audience is a mixture of laymen and scientists and very experienced tech investors and other. Just give us that sort of layman's view on what does it mean, and what is it that it offers the climate challenge?
I'll tell you about kind of the two branches of our technology. So when you think about photocatalysis and Syzygy, you should think about these two things, and they are the catalyst, and that is the special nanomaterial that we use to perform chemical reactions. And then there's the reactor. And the reactor is like the chamber, the vessel that is built to hold that catalyst and give it the conditions that it needs to work. So our catalyst is a nanoparticle, very tiny. You can fit billions of them on one of your fingernails. And the true innovation behind what we're doing was developed by professors Peter Nordlander and Naomi Hollis at Rice over the course of 30 years. And they researched this field called nanophotonics, which is how light interacts with ultra small scale structures, and eventually created a near perfect light harvester. It is just incredibly good at grabbing photons and turning them into what's called a plasmon. Recently, they started doing work where they're decorating those with traditional catalysts, and it turns out that the plasmon can activate traditional catalysts. These are the things that are used in, big chemical refineries, et cetera, today, can activate those very well. So we have these nanostructures that catch photons, transfer the energy to the catalyst, and makes the catalyst perform just, off the charts. So we take this special material that was, really invented in 2016. And what Syzygy does is the second part. We build this structure around it. And how we energize our photocatalyst, which uses light, instead of heat, is that we have tons and tons of LED diodes inside our reactor. So it is the highest LED packing that we're aware of, and we use incredibly powerful diodes. So when we turn all the lights on in our reactor, it is one of the brightest things on the planet. And to the best of our knowledge, it is the brightest steady state condition, like condition that's meant to operate for years. It's the brightest steady state condition on Earth. And so we put our catalyst in there, we turn the lights on, and it energizes it. Why this is cool is in a traditional chemical reactor, you have to burn fuel. That burning fuel does two things. It produces lots of carbon emissions, which are bad, but it also means that you have to build the whole reactor out of really expensive materials, things like nickel, chrome, etc. In Syzygy, because we're using light instead of heat, we can build our chemical reactors out of things like aluminum and glass and plastic, which are just dramatically cheaper. And so where the burners are in a traditional chemical reactor, that wall is where our LEDs are, and it's like 800 degrees Celsius, 1200 degrees Celsius in a traditional chemical reactor, and it's like room temperature and atmospheric pressure in ours. So completely different classes of materials, and LEDs are super efficient. The catalyst works really good. So not only do we get this dramatic reduction in CapEx because of the very high efficiency, we also have really low operating costs. So we take this and we do things like make hydrogen, we turn CO2 into different things, and all the fun things. I'm sure we'll get more into that in the podcast.
As it happens, earlier today, I was having a conversation with one of the big chemical manufacturers, and they were talking about, their big decarbonization challenges, and they were talking about the big challenge for them being high industrial heat needed to crack ethylene, to create other products then from that. So could this be at some stage something that would step in instead of that kind of fossil fuel high intensity reaction? Is that where it could step in, or is it slightly different?
100%, you are on the money. That is exactly it. And so for these chemical reactions that they need at mega scale, so like huge industrial chemical and petrochem, they need that high industrial heat. And with our specialized photocatalyst, we can make, by changing up the catalyst formulation, we can make catalysts to do reactions like that. In fact, one of the first papers that we found on the technology was doing work with ethylene. So it's a molecule we're familiar with. And some of the reactions that we're doing today are potentially more challenging than the reaction. I can tell you there's a handful of reactions we can do today that are way more challenging than the reaction you're talking about. And so long term, we plan on taking this huge chemical value chain and helping to electrify it. And so replacing the combustion needed for that reaction and the hundreds of other reactions that are going on in these operations, replace the combustion needed and eliminate all those carbon emissions and allow those processes to run on renewable electricity. We feed that renewable electricity into LEDs and they do all the work. And so they and the catalyst do all the work. So you're right on the money. Where we're planning on starting is with hydrogen production. Hydrogen's hot right now. So we can make hydrogen from two different feedstocks. They are methane and ammonia. And so those are the two feedstocks we're using to make hydrogen. When we make hydrogen from methane, it's photocatalytic steam reforming. It's very similar to traditional steam reforming, just no combustion. So you eliminate the flue gas, which is a pain in the butt to deal with. You eliminate all that infrastructure to handle that. And the CO2 that is made is very highly concentrated, because you basically make, through the process, you make like hydrogen and CO2, you pull all the hydrogen out. So you have this really concentrated stream of CO2. Let's remember that. I'm about to come back to that in a few minutes. That relates to Decarb Connect. So the other way to make hydrogen is from ammonia. Now, ammonia, NH3, there's no carbon atom attached to it. So it's very interesting from like an energy carrier standpoint for the future. And nations that have to import their energy, countries that are like importing LNG today, almost all of them are evaluating ammonia as like what comes next. And so our capability to take that ammonia and turn it back into hydrogen is very interesting. The idea being you make the ammonia somewhere like Australia where energy costs are low, and then you ship it somewhere like Japan or Korea, and you then use our technology to get the hydrogen back out. So last reaction, and I'll toss it back your way. And that is, I said, we create that highly concentrated stream of CO2 when we're working with methane. Well, our third technology that we're bringing to market under a National Science Foundation grant is CO2 to syngas. And so we're taking CO2 and combining it with a little bit more methane, and we make a syngas ratio. And we're planning on taking that to methanol. And so you're talking about CO2 to fuels and CO2 to value in the future. A very, very powerful process. The economics of doing this are really good. You can achieve negative carbon intensity under many different scenarios. And in fact, if you're using renewable methane and like CO2 from some kind of industrial source, it actually is the most carbon negative reaction that it is possible to do. So we're very excited about that. And combining that with the hydrogen production, you can get a system where you're making like hydrogen and methanol with no emissions going into the atmosphere. The carbon intensity looks amazing. The economics look amazing. Customers are like falling over themselves to get in line.
But so you mentioned obviously that the main kind of industry we talked about there right off the bat was chemical industry. What are the other industries that you see stepping up to you around this? I know all kinds of industries can use what you're talking about, but who do you see as your sort of, I don't know, priority hit list? What are the sectors of real strategic interest for you?
Yeah, so I'll talk a little bit about our business model, and I'll talk a little bit about the uses for chemicals, because as a chemical reactor developer, all of our applications feed into the industrial gas, chemical, or petrochemical and fuels industries. And how we plan on working with others there, we're best in the world at making photocatalytic reactors, and others are better than us at making huge plant operations and running giant hydrogen production facilities and capturing CO2 and working with it. And so we want to be a technology licensor and a solutions provider to those who want to like engage with the energy transition and quit burning fuel and producing emissions. So we would work with like an EPC, partner with an EPC to build a plant for an operator, and we would like license our technology and sell the reactors into the plant. But others would handle the big plant. Those big plants, so hydrogen production feeds into petrochem, ammonia manufacturing, methanol production, and steel. So those are kinds of the applications that you can hit with hydrogen. It also feeds into transportation a little bit, which is interesting and growing area. That's a different kind of animal though, because the first four I mentioned, these giant, massive facilities, and transportation is like small and distributed, which our reactor is also good for. So we can touch transportation through that. And then on the CO2 to value or fuel side, you need a CO2 source. And so you're either using some large industrial source, like one of those plants we mentioned earlier, like cement production, something that's making a lot of CO2. So that's one source. The other source is potentially DAC, direct air capture. And there is growing interest around that, but I think that's going to take a little longer to come online in a big way.
I said at the start, I was interested to revisit that initial search for the original technology that you did. You sort of broadly painted this picture of we were on the hunt for an early stage tech that had an answer within the energy transition space. So when you think back to that time, what were the most obvious things that you were really looking for, and what were the things that were easy to discount? Because there's a lot of early stage technology in this space, right? So there must have been quite a lot for you to consider. So how did you go about refining that, and what was it specifically about this approach that really grabbed hold of you?
Yeah, if I were to like name our approach, I would probably call it like battle royale, because it's very much like throw a bunch of ideas into an arena and see which ones don't survive. And so you're constantly trying to kill whatever idea you have, because if you can find a reason why it won't work, you want to know that on like day one, so you can stop focusing on that and start focusing on something that will. So we developed a framework, TMI, technology, market, and impact. And so we would assess the technology. We'd look at like, the lab that it was coming out of. Are they credible? Do they have a good track record? Like, what publications has this been published in? Do they have any patents? Have they started any other companies? we would look at how the technology compares against other technologies. Like, oh, it's in this industry. And we didn't limit this to just energy. We were also looking at like med devices, so I remember one technology we were looking at was for like shoulder and hip implants. And those, we looked at it and it's like, okay, because of material problems, they typically break down after like 10 or 15 years and you have to get it replaced. But this one could potentially the material was amazing. And so you could potentially make one that could last like 70 years. And so we were like, oh, that's amazing. I think Johnson & Johnson ended up like grabbing that. And so the university we were talking to, we were like, yeah, let the big fish have that one. But yeah, we'd assess the technology, we'd compare it against how it is in the market and kind of look at its pedigree. Then we'd look at the market, if we make something, will people actually buy it? And how much will people buy and how often? And, we do customer discovery and we'd call some people and ask them, hey, if we could make this thing, would you be interested? And people are like, yeah, tell me more. It's like, okay, we've got something. And if they just like if everyone just hangs up on you, then maybe you don't want to do it. So, assess that. And finally, impact. We wanted to find something that really did good for the world, like going back to like med devices. If you can find an implant that never needed to be replaced, that's like good for humanity, like reduces suffering. We're also very interested in energy transition and climate change. We're looking at a lot of technologies there too. I'd say it was about like a 90-10 split. 90% of the stuff we were looking at was like energy and climate change related and 10% other things. We looked at like thermoelectrics, concentrated solar power. We looked at different operating models around deploying solar panels. We looked at like all kinds of things. And eventually we found this photocatalyst, really intense technology. Like no one had ever made photocatalysis work before. So we were incredulous from day one. But we started talking to the professors. You start like looking at what they've done. And you're like, oh, this is completely different from other photocatalysts that came before this. Then you start looking at the metrics. Like there's like a metric called catalyst activity, and it's like how much unit of product you can make per unit of catalyst per time. In a refinery, their catalysts are in the like high hundreds, let's say, for this metric. Traditional photocatalysts are like 20, 30, low tens. When you look at that gap between traditional photocatalysts and like refinery grade catalysts or chemical plant grade catalysts, like the gap is so big, it will just obviously never work. And then so traditional photocatalysts, like 20s, 30s, refinery catalysts, like high hundreds. And then we find ours and it's like, boom, like 4,000, like it's off the charts. And we're like, what does that mean? Like, we don't know. So we get excited and then it's cheap to make, easy to scale up production of the catalyst. The only reason we can find that it won't work like is that, no one's making these structures to use it. No one's making photocatalytic reactors. So we start looking at, business models like, oh, because it's low temperature, it can be built out of super cheap stuff. It just keeps getting better and better and we can't kill the idea. So then you have to quit your job and do it, which was a whole other story. That's how we eventually came to this selection.
And so you narrowed that down. Just remind me, what year was it that you first identified this?
Oh, we started the technology search back in like 2015, and then in 2016, we really were cranking through it in summer of 2016. Like, I don't know, 10 to 20 technologies a month that we would look at. Some of them you can kill really fast. Like, oh, that is, you see all those papers like, oh, scientists invent like new thing that does this, but then you never see it in the market. So like we would go look at that stuff. We get super excited by the hype articles. Then we'd like look at the paper and we're like, oh, this is not as good as it sounded. So that was like summer 2016, found our first paper from the Hollis group in late 2016, evaluating it through early 2017, left in early 2017. Took us about 12 months to raise the first round. That was, that one put some years on me. I lived like 5 years in 12 months. It was fun. Got that first fundraise done, grew to 5 employees, scaled the tech pretty dramatically. At that point, it was obvious that like in the very beginning, it was like, will this even work? Will Mother Nature allow us to replicate these kind of results at a bigger scale? And like, we answered that with the first fundraise, like, yeah, Mother Nature, there's nothing from Mother Nature holding you back. And so it's like, okay, the science is like really strong. Then it gets into like, can we engineer a product around it? And so we like raise 10 million bucks, and then we double our metrics. Like everything gets way better. And so then we go raise, that was in 2019 when we raised that, and we go raise like, another, good chunk of money in our Series B, just under 24 altogether. And that was in early 2021, about a year ago. And that's to accomplish the final step of like refining things and turning it into a product that can be given to a customer. And then going to fundraise again. And that's going to fund like actually like deploying first projects with customers.
Okay. So you've had this kind of nice, kind of the good, like that, the healthy rhythm of investment that everyone wants to see, right, for an early stage technology, that it's kind of regularly lifting up to the next phase. So what now? I know that when we were talking in prep, you were saying you're sort of targeting, I think it was 2024, I have here, as the year when you really want that kind of large scale order to take off. But what happens between, where are we now, end of February 2022 and 2024 to get to that stage?
Yeah, so if everything goes according to plan, which the past couple of years have taught us that it always does, being a bit sarcastic, but everything goes according to plan, we should be deploying a reactor in, somewhere on Earth with a customer in 2023. We're in late stage conversations with a number of potential clients from different parts of the world. We are designing that reactor right now. We have named it Rigel, and that is like the size that we want to go to market with. So build that through the end of this year and ship it to a customer, mid next year. Then from there, we have to do the next scale up, which is we need to put multiple of them together. One Rigel reactor is, pretty sizable. Like if you're making hydrogen, we're anticipating like, 150 to 200 kilograms per day kind of sizing. You put, 10 of them, together, and you're making tons per day. And so the next scale up is to do that, put like 5 of them together, 10 of them together, and get to that like ton per day production level in a module that we call a reactor bank, and deploy that in 2024. And that's kind of the last like proving point. At that point, there's really nothing else to prove. And it's all about just scale and execution. So, we want to build out that mass manufacturing capability in 2024, because we put a reactor bank on the ground in 2024. We've got like reliability, run life data on the reactor. We know how they work. We know we can deploy them. We know we can put them together. Then it's time to start talking big projects where people are putting, 100+ reactors together, and probably be ready to deploy, given how long those kind of projects take to line out and build and everything. Probably be, signing agreements for that in late 2024, 2025, and, trying to bring that plant online and commission it for the first time, like post 2025.
And then one challenge that sometimes comes up for some early stage technologies, perhaps not yours, because as you say, you can work with well-known cost-effective materials, but is there any kind of supply chain challenge that you've got lying ahead of you in terms of when you get to that scale? Is there anything that you're like, yeah, we've still got to nail XYZ? I mean, you're not looking for rare earths, I don't think, are you? I don't know. Sorry, I said that very assumptively. Maybe I shouldn't.
No, our catalyst is, like I mentioned, it's a platform technology, and it's got some pretty unique properties. So we can actually change like what materials we make the catalyst out of. So like material concerns aren't big for us at the moment. On the like reactor supply chain side, catalyst aside, on the reactor side, like aluminum, a lot of people are using aluminum, but it's not like it's going away. Price is going up, but it's still 20 times less expensive than nickel, whose price is like absolutely skyrocketing. The glass we use, because we use light, you got to use glass to let the light through to get to the catalyst. No, there's not really any shortage of that. We do see, like with what's happening around the world, we do see lead times going out. Like, so some things that, used to have a lead time of 4 weeks now have lead times of like 8. Some components can have lead times up to like 16 weeks, but like this is all manageable, like with a good supply chain strategy. There's nothing like if you're in auto and you're thinking about like the current chip shortage, like it's kind of a big deal. It's really limiting your ability to grow. We don't see anything like that in our near future.
One of the things that, just from my perspective, really sets you apart is that you came from this R&D background. You came from that corporate world of looking at ideas, working out how to scale them, pushing through project boundaries, discarding at key points. That's pretty unusual, isn't it? I would imagine that quite a lot of the founders and co-founders that you've met along the way in clean tech were probably the people that were bringing this baby to life from their grad studies onwards. So I'm just kind of interested in what's your perspective on the pros and cons of that, or how that makes you different?
I mean, it definitely does make us different. It is not something I run into very often. The founder story you're talking about, where they go to grad school and get their PhD and do their research in this area, and they love it and they want to see it get to market. It is fantastic origin stories. I love those. Ours is, and I'm not saying that's bad, but like ours is just very different because we're brutal. If we found something that we knew would handicap us, that we could not overcome, that original battle royale mentality never left. If I found a reason that our photocatalyst couldn't make it, I would go find a company that could, or find a technology that could. And so that original brutal mentality is still there in this. And the truth about the technology is that the development and scale up has just been like phenomenal, amazing. And we have a dragon by the tail. We've never seen anything like this. And having looked at dozens of things, we have a very unique perspective on technology. Because whenever I see competition and things like that, I'm always like, oh, I could go do one of those companies if that's going to be the thing that goes the distance. But for the life of me, I can't find another thing that seems to have as much in-game potential as ours does. Like hydrogen, there's some things that are going to disrupt hydrogen. And there's some things in hydrogen that in certain scenarios will give us a run for our money. It's going to be a good fight. CO2 processing. Actually, we got a really strong edge in CO2 processing, but there's some good technologies out there. Get into ammonia production and ethylene and all these things, and all of a sudden you're like, oh wow, this is one of the only technologies we've seen that can just like weave through all these different things that are like fundamental, pillars to human society: fuel, fertilizer, raw materials for all the products you see around you. We went looking for something like this and we found it. So I think that broad spectrum approach has been very influential and does give us a little bit of a feel for this that others don't have.
So you sort of laid out that sort of broad spectrum of applications that you can potentially feed into. You've laid out sounds like an incredible technology, and the scale up, whilst I'm sure has not just been as easy and straightforward as as it sounds, it's clearly been a relatively upward trajectory, and it's been a great experience. What's the kind of call to action now? So you sort of mapped out who you are, what you are, where you're heading for. What's the call to action for the people listening? Who do you want to hear from? Who do you want to engage with?
If you are a company that is looking for very low cost clean hydrogen solutions, you should talk to us. If you are a company that has a CO2 source and you want to do something about that CO2, and you're interested in evaluating turning that CO2 into a raw material for a product, utilizing it to create fuel or methanol or something else, you should talk to us. And if you're interested in other reactions that are in gas phase, I think that's an important distinction. If you're interested in other gas phase reactions, developing new catalysts and eliminating emissions associated with them, you should come talk to us, because we are developing new catalysts all the time. If you're interested in deploying cutting edge tech, definitely give us a call.
Well, anyone that is curious and who's able to get to Houston at the end of this March, that's March 2022, Trevor is joining us there, so you can come and pick his brains and put him under the microscope, etc. But otherwise, Trevor, thank you so much for kind of walking us through that, and can't wait to see where Syzygy goes. But yeah, good luck. Great to have heard from you.
Thank you, Alex.
Many thanks for listening to the Decarb Connect podcast. We work with clients across the industrial sectors, specifically those who are tasked with decarbonizing the most energy intensive products and materials that we use every day. If you have an interest in learning more about either our members network, our reports, or our event series, do get in touch with us at decarbconnect.com. Or if you'd like to take part in the podcast, email me, Alex, at ac@decarbconnect.com. Thanks for listening.